September the 12th, 2025. Astronomers detect something that shouldn't exist. A colossal object streaking in from deep space, tail stretching 5 times the width of a full moon, dwarfing anything seen in decades. Within hours, a second visitor confirmed, both racing toward the sun from opposite corners of the sky, arriving mere weeks apart. The odds of this cosmic double entry, according to experts, astronomical. The official story, twin comets. But the evidence points to something deliberately engineered. Everything we thought we knew about comets? Wrong. September 12th, SOHO's SWAN instrument catches it first. A bright streak, unmistakable, blazing through the solar system. Initial data pours in. A tail stretching nearly 2.5 degrees across the sky, 5 full moons laid end to end. Magnitude 7.4, bright enough for backyard telescopes. Within 48 hours, amateur astronomers in Australia capture a dramatic image. Light so intense it threatens to spill out of the camera's field. The International Astronomical Union makes it official. See 2025 R2, tagged SWAN. But here's what they're not saying. Most modern comets are faint, requiring massive observatories just a glimpse. SWAN? Visible to anyone who knew where to look. Its tail sliced through Virgo, growing brighter as it closed on the sun. The initial reaction wasn't excitement, it was disbelief. The numbers didn't fit any precedent. As reports piled up from observers across hemispheres, one thing became clear. SWAN was physically dominating the inner solar system in ways not seen since Hale-Bopp, or further back. And it gets stranger. Just days before SWAN's discovery, another object, Three-Eyed Atlas, was already inbound from a completely different sector of the sky. SWAN's path traced back through Aquarius. Atlas entered from Sagittarius. On a star map, these arrival vectors are separated by more than a quarter of the celestial sphere. Yet both objects set to reach perihelion, closest point to the sun, within the same 10-day window. For SWAN, that moment, October the 20th, at 150 million kilometers. For Atlas, October 17th, just 3 days earlier, at 203 million kilometers. That puts their perihelion points only 50 million kilometers apart, closer than Mars ever gets to Earth. This isn't just overlapping dates. The geometry is striking. Both objects on steeply inclined orbits. SWAN's path tilted more than 60 degrees off the ecliptic. Atlas nearly perpendicular to the plane of planets. Their approach angles so different that by chance alone, the odds of both crossing the inner solar system at almost the same time, at such similar solar distances, vanishingly small. Astronomers who track long-period comets are used to randomness, arrivals scattered across the calendar, perihelia spread over months or years. But here, the two brightest new objects of the decade converging on the sun in near synchrony, each from a different corner of the sky. Atlas broke the rules. Early spectrographs from the Atlas Spec Lab reported something that set off alarms. A body dominated by nickel with virtually no iron in the mix. That runs counter to everything known about comets, which almost always show iron-nickel blends in their vapor. The claim was so unexpected, some labs immediately called for data to be rechecked. A calibration controversy spilled onto astronomy forums, triggering waves of independent reviews. The debate only intensified with the next round of measurements. Instead of classic water vapor signature, Three-Eye Atlas's coma pumped out carbon dioxide at rates 5 times higher than water. The 4.3 micron CO2 line dominated every spectrum. H2O barely registered above noise. That's rare, but not unheard of. What couldn't be explained away? The behavior of the tail. Observers tracking Atlas's motion noticed a pattern. 3 distinct accelerations, each spaced roughly 2 weeks apart, each coinciding with a sharp change in tail color. First pulse logged July 29th, second, August 14th. Photometric data showed sudden jumps in brightness while spectral slope shifted from reddish to nearly neutral, then back again. These so-called delta V pulses weren't smooth like gradual push from solar heating. They came on fast, then faded, as if the object had fired a thruster, and Atlas did something no comet should. Peer reviewers pushed back, pointing to risk of calibration drift or hidden systematic errors. But the Atlas Spec Lab team defended their findings. The timing and magnitude of pulses matched across independent observatories, from the Averroes Tracker Network in Spain to Bill Gray's Distributed Telescope Array. Bill Gray, a veteran orbit tracker known for open-source calculations, had been watching this unfold with growing concern. The numbers didn't behave like typical outgassing, he told colleagues in encrypted chat rooms. The tail's CO2 mix seemed to modulate in sync with each acceleration, a phenomenon some called thrust mix modulation. What really set the rumor mill spinning? The energy estimate. If the observed accelerations were real, the implied power source inside Atlas would need to deliver something on the order of 10 gigawatts, about the output of 10 large nuclear plants, far beyond what any known comet nucleus can muster. The mainstream view still holds that natural processes can account for most of the data, but the gaps, especially the nickel-only spectrum and the stepwise accelerations, have kept the engineered object hypothesis alive. But Atlas isn't alone. C 2025 R2, now simply called SWAN, stands in a league of its own. The numbers tell the story. A tail stretching 2.5 degrees, a brightness peak rivaling the best comets of the last century, a core that, if the wildest estimates are even close, could be pumping out 10,000 gigawatts of energy. That's more raw output than the entire power grid of Earth, and then some. But it isn't just the scale that has people talking. It's the claims coming from the fringes of the astronomical community. Claims that SWAN is armored, shielded, and powered in ways that stretch the limits of current physics. SWAN doesn't behave like anything we've seen. The first whispers started with reflectance data. Standard comet nuclei scatter sunlight in predictable ways, but SWAN's core reflects light with a sharp metallic signature. Some amateur spectroscopists argue this matches not just nickel, but a nickel-cobalt blend, materials chosen on Earth for strength and resistance to corrosion. The term nickel-cobalt hull began circulating in chat rooms and late-night podcasts, fueled by the object's stubborn refusal to break apart or dim as it closed on the sun. Then came reports of an optical anomaly, a persistent silvery halo around the nucleus, shifting in pattern and intensity. To some, it looked like a plasma envelope, a kind of electromagnetic shield that could deflect solar wind and cosmic debris. That's where the Fortress nickname comes from. Unlike 3i Atlas, which acts more like a drone, quick, agile, oddly efficient, SWAN presents as a tank, slow, steady, seemingly invulnerable. Then SWAN appeared and dwarfed everything. The tail, already record-breaking in length, pulses with microthrusts that defy simple outgassing models. Photometric analysis shows tiny rhythmic changes in tail direction, as if the object is making course corrections with precision bursts of plasma. Each pulse registers as a blip in brightness curve, and the pattern repeats with regularity hard to chalk up to random surface eruptions. The orbital numbers add another layer. SWAN is on a path that will take it around the Sun once every 22,554 years, a cycle so long it brushes up against the last ice age. Everything we thought we knew, wrong, because SWAN's 22,554-year orbit means it was last here during the Ice Age, when humans first started watching the sky. If this object is engineered, it's been on a preset course for longer than human civilization has existed, and yet it arrives now, at the same time as Atlas, in the same solar corridor, during a window when Earth's telescopes are blinded by the sun. The odds of all these factors combining by chance, vanishingly small. Then the orders came. From October 8th to 18th, every major ground-based observatory faces a hard stop. Official schedules list the window as solar conjunction downtime. But behind the scenes, the restrictions go further. Internal memos from U.S. Space Command and the European Space Agency direct teams to suspend all radar and high-resolution imaging of both SWAN and 3i Atlas during this blackout. Some proposals for alternative coverage denied without explanation. Requests for raw data quietly rerouted or delayed. A handful of telescope allocation reviewers, speaking off the record, describe explicit orders to avoid public statements about either object until after perihelion. The blackout wasn't accidental. a forced silence at the very moment when the two most unusual visitors in decades crossed the sun's glare, leaving only a narrow band of independent astronomers and amateur networks to fill the gap. When the blackout orders hit, official channels went silent, but the amateur networks did not. Bill Gray started rallying a distributed web of backyard astronomers and small observatories. His call went out across public forums and encrypted chat rooms. Keep your scopes on the sky. Log every flicker. Share the raw data before it disappears. The Ibero Tracker Collective in Spain and Portugal began pooling wide-field sensor feeds. Leaks from private astronomy groups suggested makeshift plans to bypass the blackout using radio telescopes and even repurposed weather satellites. With government agencies off the record and big observatories locked down, the grassroots effort became the only line of defense against a total information vacuum. Anyone with a telescope, a radio dish, or access to open-source tracking software could join. The blackout window wasn't just a challenge. It was an invitation. But there's a third possibility. Every major anomaly logged for SWAN and 3II Atlas has turned the conversation from what these objects are to what they might be doing. When two massive bodies, one on a 22,554-year return, the other on a hyperbolic, possibly interstellar path, arrive nearly together, the odds of pure chance drop off a cliff. The timing, the geometry, and the blackout window have all fueled a wave of mission theories. One possibility looks almost routine, at least by cosmic standards: scheduled maintenance or refueling. In this scenario, the sun acts as a pit stop. Both objects could be engineered to use solar energy or magnetic fields for recharging, data handoff, or even systems audit. The idea isn't far-fetched in deep space mission planning. On Earth, solar flybys are standard for gravitational assists and energy boosts. If these objects are probes, the sun is the logical place to top up or exchange information. Another theory is less peaceful. The close approach could be an intervention, a rendezvous to recover or neutralize a malfunctioning unit, or perhaps a contest between rival factions converging on a resource. The power levels estimated for each object: Atlas at around 10 GW, SWAN at a staggering $10,000, suggest the kind of energy reserves needed for active maneuvering. Not just passive drifting. Stepwise accelerations and tail modulations in Atlas, micro-thrust pulses in SWAN, all hint at a level of control that fits with a mission profile, not random outgassing. There's also the audit chain scenario. Oumuamua in 2017, followed by Atlas, and now SWAN, could represent escalating responses to Earth's century of radio transmissions. Each new arrival would be a more complex probe sent to check in, gather data, or escalate contact. In all three frameworks, the sun isn't just a backdrop. It's the power node, the rendezvous point, the beacon, and the cycle goes back farther than you think. A 22,554-year orbit is more than just a number on a chart. It's a cycle that reaches deep into the last ice age, when the world looked nothing like it does today. Around 20,000 BCE, glaciers covered much of the northern hemisphere. The climate was shifting in ways that shaped the earliest chapters of human civilization. That same epoch left its mark in the ice cores of Greenland and Antarctica, where layers of dust and tiny chemical changes hint at sudden, dramatic events in the sky. Some researchers have pointed out these layers line up with periods when bright, long-period comets could have swept through, leaving not just debris, but stories that might have echoed down the generations. At the heart of this idea is a place called Göbekli Tepe, a site in southeastern Turkey built more than 11,000 years ago. Its stone pillars are carved with animals and abstract symbols, but among them are motifs that some believe show the paths of objects in the sky, possibly even comets. A handful of theorists argue these carvings record cycles far longer than a human lifetime, maybe even marking the return of something like SWAN. The mainstream view is much more cautious. Archaeologists and astronomers alike warn that these connections are speculative at best, built on patterns that could just as easily be chance. The debate is heated, with critics pointing out that no direct evidence ties these ancient monuments to specific astronomical cycles. Coincidence or warning? Still, the timing is hard to ignore. If SWAN really does return every 22,554 years, its last swing through the inner solar system would have happened just as the world was emerging from the grip of the glaciers, at a moment when human culture was taking its first steps toward building monuments and tracking the heavens. Whether that's coincidence or something more is an open question, but it adds a layer of mythic resonance to an already extraordinary event. Same epic, same pattern, same silence. October 8th, the sky goes dark. From October 8th to 18th, the official narrative is simple. Solar conjunction makes observation impossible, but that's not entirely true. In Australia, just 2 days after the satellite alert, an observer captured a dramatic image of SWAN, a streak of light so long it threatened to spill out of the camera's field. The image was uploaded to public forums within minutes, tagged with coordinates and exposure settings. Within hours, dozens of amateur astronomers replicated the observation. The Atlas Spec Lab team, still defending their controversial nickel-only findings, began coordinating with Bill Gray's distributed network. They set up automated alert systems. Any brightness change, any tail modulation, any spectral anomaly would trigger immediate cross-verification across multiple observatories. Government labs stayed silent. Amateur networks lit up. The blackout orders were explicit. Telescope allocation reviewers, speaking off the record, described being told to minimize public speculation and defer analysis until post-perihelion assessment. One reviewer who requested anonymity said, "It felt less like scientific caution and more like damage control, unless you know where to look. If the first signals come when SWAN and Atlas reemerge, they might not come from NASA or ESA. They might come from someone's backyard in Portugal, or a repurposed weather satellite in Spain, or a radio telescope in rural Australia operated by 3 grad students and a Reddit thread." The blackout window wasn't a shutdown. It was a shift in power. The last time this happened, we carved it in stone. The facts are clear. 2 anomalous objects entered the inner solar system together, defying statistical odds and raising questions no agency has answered. SWAN, a fortress with a 22,154-year cycle, energy output rivaling Earth's power grid, possibly shielded by plasma. Atlas, a drone with nickel-only composition, CO2-dominant outgassing, and stepwise accelerations suggesting active control, both arriving within days, both from opposite corners of space, both during a blackout window when official channels went silent. The sun isn't just their destination, it's the rendezvous point, the power node, the beacon. Whether this is scheduled maintenance, an intervention, or the next step in an escalating audit chain triggered by our own radio emissions, we don't know yet. But we will. The amateurs are watching, the data is flowing, the silence won't last, and when they re-emerge, we'll know. Turns out the biggest threat to government secrecy isn't hackers. It's hobbyists with telescopes and too much free time. When they re-emerge, what will we see? The first signals might come from someone's backyard, not a government lab. Subscribe so you don't miss the next shocking chapter.